If you're a Rust developer, you have to watch this video, because even though Rust is fast, it doesn't mean your Rust code is fast. If you don't know how to profile and optimize your Rust code, then you're only scratching the surface of what Rust is capable of. So in the next 12 minutes, I'll show you exactly how to squeeze out every last drop of performance from all your Rust applications. We'll cover the performance tuning lifecycle, all the important Rust tools and frameworks you'll need for performance profiling, and the key strategies and techniques you can use to make your Rust application blazingly fast. This video is part of a series for the upcoming official launch of my Rust Live Accelerator program, the all-in-one Rust Live training program designed to help you land your first Rust job and become a high-performing Rust developer. We'll start accepting applications soon, and we only have 25 spots available. To join the early access waitlist, pause this video right now and visit letsgetrusty.com/join. Part 1. Measure, Isolate, Optimize. Donald Knuth, a legendary computer scientist, famously said, "Premature optimization is the root of all evil." But this quote often gets misinterpreted. The full sentence states, we should forget about the small inefficiencies, say about 97% of the time. Yet we should not pass up the other opportunities in that critical 3%. You see, the problem isn't optimization, it's optimizing the wrong thing. Which is why the first step in the performance tuning cycle is to measure performance and see where your app is spending compute and other resources. Only then can we isolate the bottlenecks and optimize them away, using strategies and techniques which we'll talk about later. But first, what should we be measuring anyways? In performance critical applications, there are 5 key metrics that we typically need to pay close attention to. Note that these are runtime performance characteristics, but in some niche cases, for example, if you're writing a library, you might also care about the compile time performance of your code. Luckily, Rust is already known to have great compile time performance. Alright, now we know what we're looking for, so how do we actually measure it? There are so many different tools out there that it can feel extremely confusing and overwhelming. Luckily, in this video, I'm going to give you a collection of tools that are easy to use, work on all major operating systems, and as a bonus, are written in Rust. I'll also share a set of tools for profiling async Rust code, so make sure to stay tuned. Okay, let's start profiling. One very popular use case for Rust is implementing data processing pipelines. In fact, I've seen this done in production at multiple companies. So for demonstration purposes, we'll be profiling a data processing tool. We'll be measuring the performance of a CLI tool that ingests HTTP log files, parses them, and spits out useful summary data. Here's the tool in action. We'll build a binary in release mode to take advantage of all the optimizations the compiler provides. Then we'll call the binary and pass in the log file. This gives us a nice summary of the logs. We can see the total requests, the top endpoints, peak requests per second, and more. So how do we measure the performance of this application? The first tool we'll use is called Hyperfine, a command line tool that allows us to easily benchmark our application. Once Hyperfine is installed, we can call Hyperfine with the command to execute our binary. Our app takes around 460 milliseconds to run. Great, so we now measured performance and established a baseline. But we need to go a bit further and isolate which parts of our application are taking up the most CPU time. To do that, we'll use another fantastic tool called Cargo Flame Graph, a Rust-powered flame graph generator. After installing it, we can run Cargo Flame Graph and pass in our binary. This will generate an SVG file we can open in any browser. But notice we get a warning. Profiling without debug info enables symbol information by adding the following lines to cargo.toml. By default, release builds don't include debug symbols, which would make it really hard for us to read the output. Let's fix this by opening up cargo.toml and enabling debug symbols in release builds. Then we'll build in release mode again and rerun Cargo Flame Graph. Now we can copy the Flame Graph SVG path and open it up in a web browser. Here we can see exactly where our application is spending its time. 99% of the time is spent in the main function, which is not surprising because the main function captures the duration of our entire program. But if we look at what's happening inside main, we can see that about 50% of the time is spent calling from iter to transform an iterator into a vector. We'll note that down for later. Now, besides seeing where CPU time is spent, we also want to understand how our application is allocating memory to detect potential wasteful memory allocation and usage. To do that, we'll use a tool called dhat, which provides heap profiling. First, we'll add dhat as a dependency, and then we'll also add a new feature called dhat heap. Then inside main.rs, we'll configure our application to use the dhat global allocator and profiler when the dhat feature is enabled. Now all we have to do is run our application with the feature enabled. This will produce a JSON file which we can view online. We can see that our app allocated 546 million bytes, or close to half a gigabyte in total, which is pretty huge. And 82% of those allocations are coming from calling collect to turn an iterator into a vector. So now we know that vector allocation is taking up most of our CPU time and memory. By the way, one thing that could be really helpful is to pass the files generated by Cargo FlameGraph and dhat to LLMs, and have them analyze the performance bottlenecks for you. Although it's not perfect, this could be a great starting point if you're new to profiling. So Hyperfine, Cargo FlameGraph, and dhat helped us understand the performance of this synchronous application. But if you're profiling async code, then you'll also want to use the following 3 tools as well. Tracing is a framework for collecting structured, event-based diagnostics in Rust. And with subscribers like Tracing Chrome and Tokyo Console, you can visualize and analyze async runtime behavior to spot bottlenecks. Tokyo Console works with tracing to give you real-time insights into your async task execution, showing you when tasks are spawned, woken, or completed, making it easier to debug slow or stuck features. And Ohio is a fast, Rust-based CLI tool for load testing HTTP endpoints, with a simple terminal UI and high performance. I dive deeper into profiling async code in my Rust Live Accelerator program, but more on that later. Now that we've measured our application, defined a baseline, and isolated the bottlenecks, it's time to start optimizing. Part 2. How to actually make your Rust code blazingly fast. Now, every application is different and will require unique approaches to optimizing code. So in this section, we'll walk through general optimization strategies you can use to optimize inefficiencies, starting with how to avoid using inefficient algorithms or data structures, and doing more work than required. Let's look at inefficient algorithms first. When we first profiled our application, we figured out that most of the CPU time and memory allocations were going towards converting iterators into vectors. So let's take a look at our implementation. In main, we extract the CLI arguments passed in, read the specified file, and then pass its contents to a function called parseLogs. This function processes the log file and returns a logstat struct. However, currently we have an algorithm here that takes an inefficient approach. Inside the for loop, which iterates through every line in the log file, we call the split method to split up each line into an iterator of substrings, then collect this call to turn that iterator into a vector. Finally, we're able to extract out information by indexing into the vector. But calling collect for each line is very expensive. Our sample log file has 1 million lines, which means we'll need to create 1 million vectors. This is both CPU and memory intensive. Let's go through the workflow of optimizing this algorithm. Remember that we already measured and isolated the problem for this program, which was a high number of vector allocations. Luckily for us, the solution in this case is very simple. Let's optimize this code by removing the call to collect, and instead parse each line by navigating through the iterator. Now let's build our app with the new parsing implementation. And run tests to make sure we didn't break the implementation. Previously, our app took about 460 milliseconds to run. So let's run Hyperfine again. With this modification, our app went from 460 milliseconds to about 300 milliseconds. That's a 35% improvement. But what about our memory footprint? Let's go ahead and run dhat again. Here we can see that our total memory footprint went from 500 million bytes down to only 100 million bytes, an 80% reduction. We've just completed one entire iteration of the performance tuning cycle, but this is only the start. The second pitfall we want to avoid is doing more work than required. To accomplish this, we can use caches to avoid doing expensive work multiple times, eliminate extra memory allocations by using buffers or references instead of clones. But one of the most effective ways to avoid extra work is simply to understand the requirements of your application and remove any additional work that isn't needed to meet those requirements. For example, let's take a look at a sample log file. If we know that some of the IP addresses are coming from development machines or CD/CI pipelines, then we can safely ignore them. With this in mind, we can update the parseLog function to prevent parsing IP addresses from development machines. If we benchmark our app using Hyperfine, we can see that our app went from 300 milliseconds to run to only 250 milliseconds to run, which is an additional 16% performance improvement. Now, beyond avoiding inefficient algorithms and unnecessary work, there are various techniques we can use to speed up our applications. Favoring generics over dynamic dispatch, inlining critical functions, using the copy on write smart pointer to efficiently handle data that may either be borrowed or owned, and more. But one of my go-tos is using Rayon and DashMap to parallelize work. Rayon is a lightweight data parallelism library that allows you to convert sequential iterators to parallel ones. And DashMap is a blazingly fast concurrent hash map written in Rust. Let's add both as dependencies to our project. Then we'll update the parseLogs function. Instead of creating a logstats instance, we'll define a list of atomic variables and 2 dash maps. Then we'll convert the for loop into a parallel iterator over each line in the log file. Let's go ahead and fix all the compile time errors. Now let's test and make sure we didn't break our implementation, and then build our app in release mode. Finally, we'll profile our app again using Hyperfine. We went from 250 milliseconds to 200 milliseconds, a 20% performance boost. So far, we were able to take our app from 460 milliseconds all the way down to 200 milliseconds, a 56.5% improvement. We were also able to get our memory footprint down from half a gigabyte to just 100 megabytes, an 80% improvement in memory usage. This is a good start, but of course there's a lot that goes into building production-grade Rust applications. That's why I created the Rust Live Accelerator, a private group training program where you get personalized help directly from me to become a high-performing, highly paid Rust developer. Now, because I'll personally be working with students directly, we are only accepting 25 students. So make sure to join the waitlist and be the first to know when we start accepting applicants by heading over to letsgetrusty.com/join. Hope you've enjoyed this video, get on the waitlist today, and I'll talk to you again very soon.